Hey folks, Bill Armstrong here. Taking a quick preview here of topics that you'll learn this week in week 10. When you start off in week 10 and looking at the material in the e-text, section 5.1, you're going to start off talking about exponential functions. So what I've written up here about an exponential function is an exponential function has the form f of x equals b to the x, where b is a number, where that number is greater than 0, but it can't be equal to 1. So with just that being said, b has to be greater than 0, but it can't be equal to 1. I'm going to break exponential functions into two main categories. The first one is if the base, this number here, is larger than 1. If it's larger than 1, then the graph of the exponential function is going to do something like this. And I do expect you to know this, and I would like you to know that this type of shape is called exponential growth. Okay, kind of like Bill Gates' bank account. Now if the base is a number between 0 and 1. Keep in mind the base has to be greater than 0. So for like a fraction, 1/2, 1/3, or the decimal 0.4, for a number that's between 0 and 1, if the base is between 0 and 1, then the graph is doing something like this. I'd like you to know that. I'd like you to know the name of this is exponential decay. It's kind of like my bank account. So the first thing when you start looking at these exponential functions, make sure you can recognize when you would have exponential growth. It's when the base is larger than 1. And when you'd have exponential decay. That's when the base is between 0 and 1. One observation that I'd like you all to be aware of just by looking at the graphs. Right now I'd like you to note that exponential functions are one-to-one functions. So make that a little comment in here, a little 3-star comment. They are one-to-one functions. Now I'm making that comment because since they are one-to-one functions, from prior material that you have learned, since they are one-to-one functions, that means that they will have inverse functions. And we'll talk more about that later on here in Chapter 5. That's the basics of exponential functions. Alright, let's look at the graphs of some exponential functions. I just showed you in general what the graphs would look like. Now we have a specific exponential function, the function 2 to the x. We see the base is 2. That is a number that's larger than 1. So I expect this graph to have an exponential growth type shape. If you make a table of values, you can quickly find points that would be on the graph of this exponential function. I will just kind of babble the table of values as I make the graph. So if x is 0, I put 0 in for x, 2 to the 0 is 1. So the point 0, 1 is on the graph. If x is 1, well 2 to the first power is 2. So there's another point that's on the graph. If x is 2, I put 2 in for x, 2 squared is 4. So there is another point that's on the graph. If x is negative 1, I put negative 1 in for x. Well, 2 to the negative first power, that's 1 over 2 to the first power, so it's 1/2. And I think that's enough points for me to draw the graph because, again, we had just looked at what the general shape of an exponential growth function must look like. So I get a graph that looks something like this. Nice curved exponential growth. And that's all there is to graphing something like 2 to the x. So now what if you were asked to graph the function 2 to the x plus 3. Think about stuff you've already learned about translations. I know it was on the last test. To graph the function 2 to the x plus 3, that's nothing more than the graph of 2 to the x shifted vertically up 3 units. So all I have to do is take this graph and shift it up 3 units. And if I do that, it's easy for me to just follow where these points would end up going. I mean, remember that's the point 0, 1, that's the point 1, 2, that's the point 2, 4. So if I just shift those points up 3 units, well, I'd be at 0, 4. This point will come up to 0, 4. That will go up to 1, 5. And this point here would be shifted up 3 units, so I'd go to 2, 7. And I should be able to sketch the graph. Now one thing that I'd like you to notice is on the graph of 2 to the x, the x-axis is like a horizontal asymptote as we head over here towards negative values of x, as we head off towards like the federal debt. The graph would get really, really close to the x-axis, but it would never touch it, it would never cross it. Well, think about that horizontal asymptote. If these points get shifted up 3 units, then this horizontal asymptote, it too would be shifted up 3 units. So that means that when I sketch the graph, I shouldn't cross this horizontal line, y equals 3. And by taking that into account, there's the graph of 2 to the x plus 3. I just used old information. I took this graph and just shifted it up 3 units. And that's basics on how to graph exponential functions. Be aware, or make a quick observation, this is a one-to-one function. It does have an inverse function. The domain of this function is all real numbers. The range of this function is 0 to infinity, not including 0. There'd be a parenthesis around 0. That's it for graphs. Hey, next up is something that I personally call it the preservation of equality. Your book calls it the method of relating bases. And basically all it says is that if you have a b to the x equaling b to the y, if the bases are the same, this equation is true if and only if the exponents are equal. So if and only if x is equal to y. So that's the property your book calls the method of relating bases. I will probably call it the preservation of equality. But it's the same thing as what your book calls method of relating bases. Here's how you can use this property. It's for solving equations. So let's say you're asked to solve 3 to the x minus 1 equals 1/9. Okay, somehow, some way, I want to use my preservation of equality in an attempt to solve this. And here's what I'm looking at. I'm looking at this 9. 9 is the same thing as 3 squared. So I could rewrite this mess as 3 to the x minus 1 equals 1 over 3 squared. Now 1 over 3 squared can be written as 3 to the negative 2nd power. Now check it out. My bases are the same. The bases are the same. The only way this equation can be true, when the bases are the same, the only way it can be true is if the exponents are equal. So this equation is only true if x minus 1 is equal to negative 2. And then I add 1 to both sides and I get x equals negative 1. Let's try another one. Pull it over here. Let's try solving 49 to the x power equals 1/7 to the x minus 1. Okay, I'm going to do my best to try to make my preservation of equality work. So in other words, I'm going to try to do my best to rewrite each side of the equation as some exponential looking creature where we have the same base. Kind of like what I did here in A. We ended up with the same base. So I'll start off by saying, well, I know 49 is 7 squared. So 49 is 7 squared, and then don't forget it's raised to the x power. Now in here, 1 over 7 to the first. Well, just like back here, I said 1 over 3 squared. You can rewrite as 3 to the negative second. 1 over 7 to the first power, we can rewrite that as 7 to the negative first. Now I don't quite have it in this form, but I can use an old property of exponents, that says when you have some sort of exponent raised to another exponent, so here it's a 7 squared raised to the x power, you can multiply those exponents together. So I can rewrite this left-hand side as 7 to the 2x. On the right-hand side, I'm going to use that same, it's an old property of exponents. 7 to the negative 1 raised to the x minus first power. Well, that's 7. I just multiply these two exponents together. Negative 1 times x minus 1. And negative 1 times x minus 1 is a negative x plus 1. Now check it out. I'm at exactly the same type place as I was over here in part A. I'm exactly at that point where we can use what your book calls the method of relating bases. The bases are the same. The only way they can be equal, the only way you have a true equation is if the exponents are equal. So since our bases are the same, we can only have a true equality statement if the exponents are equal. If 2x is equal to a negative x plus 1. And so to solve this friendly little equation, you just add x to both sides, and then divide both sides by 3, and that's the solution to the equation. So there's two quick examples on how to use this method to solve some equations. All right, folks, hey, the next topic, and it's kind of the last topic in this introductory section on exponential functions, is an application. It's called using the compound interest formula. This is the compound interest formula. I expect you to know the compound interest formula. The compound interest formula has all these variables in it. Now let's start to define each of these variables. First off is the P. P represents the principal. And principal is like the amount of money that you would invest. Another name for P is called present value. So it's like how much your money is currently worth. I mean, if I have $500 today, how much is $500 worth today? Its present value? Well, it's $500. Let's see, we know 1 is 1. That's a plus sign. We know what that is. R is your interest rate, and it's written as a decimal. N is the number of compounding periods in a year. So if your interest is compounded quarterly, N would have a value of 4. If it's compounded weekly, N would have a value of 52. Monthly, N would be 12. Daily, N would be 365. Semi-annually, N would be 2. Annually, that's just one time a year, N would be 1. T, see T's up here in the exponent. Notice N is also in the exponent, so it's this product, N times T. T is just simply the number of years. And then we're finally left with A. And I'll just say A is the amount. Another name for A is the future value. Let's kind of put all this into context with this example. Let's say Let's say you have $5,000 and it's invested at 3.5% interest compounded monthly. How much would be in your account after 10 years? Well, this is a classic compound interest formula problem. I encourage you for any of these to just write down your compound interest formula. Because you write it down a few times, you tend to remember it. And let's substitute in what we know. Let's see, we know $5,000 is being invested. That's the principal. That's how much is going into the account. So P is 5,000. That's the present value. So P is 5,000. 1 is 1, plus sign's a plus sign. R is the interest rate written as a decimal. Well, 3.5%. As a decimal, 3.5% is 0.035. N is the number of compounding periods in a year. So our interest is compounded monthly. 12 months in a year, so N is 12. Now my exponent, N is 12. So let me get a 12 here, times T. T is time in years. So we want to know, what do we have after 10 years? So that's 12 times 10. And hopefully you can see this exponent would end up being 120. So now if I use my calculator, and believe me, I would use my calculator, and I do 5,000 times this quantity raised to the 120th power, I get the amount to be $7,084.54. So to kind of recap all of this, $5,000 goes into the account today. That's the principal. That's the present value. That's how much $5,000 is worth today. $5,000. In 10 years, in the future, that amount, that $5,000, will have grown to $7,084.54. It's just sat there and gained interest. And that's it for a compound interest formula problem. Okay, next we look at a special type of exponential function. This is the exponential function e to the x. It's called the natural exponential function. This is what it looks like. F of x equals e to the x. And e is one of those irrational numbers. Remember an irrational number like pi, square root 2, square root 3. E is the irrational number 2.7181828, blah, blah, blah. It continues on forever and ever. It doesn't repeat, doesn't end. It just keeps going. So that's your natural exponential function. I'm going to break this down into two cases for you. Case 1 is if you have f of x equaling e to the bx. So there's some number in front of the variable up here in the exponent, like a 2 or a negative 0.3, something like that. There's just a number up here. If b is a positive number, like 2, 3, 1.4, just any positive number, so you have e to the 1.4x, the graph will be doing that. If that number here is a positive number, you have exponential growth. On the other hand, if b is a negative number, you have e to the negative 1.4x. Then the graph is exponential decay. So for the natural exponential function, the key is on the exponent. If that exponent, if that's a positive number, you have growth. If that number here is a negative number, you have decay. And see some other things to notice. Yeah, they're one-to-one functions. Since they're one-to-one functions, we know they're gonna have an inverse function. And let me write this down for both functions. The domain is negative infinity to infinity, and the range is 0 to infinity. Covers all reals, the domain, and the range is 0 to infinity. Doesn't go into negative y land. Hey, so let me foreshadow something real quick. Since they are one-to-one functions, and they do have inverse functions, knowing the domain of this function is negative infinity to infinity, and knowing the range is 0 to infinity, we know that whatever the inverse function is for this exponential function, whatever its inverse is, it must have a domain of 0 to infinity, and it must have a range of negative infinity to infinity. That's a property about functions and their inverse functions that we saw in the prior chapter. That's the basics on the natural exponential function. Natural exponential function, the base is e. Well, since we've introduced the natural exponential function, it's only natural we look at solving some equations involving the natural exponential function. And again, all we're going to do, we're not going to use anything new. This is old material that we just saw, the preservation of equality, or as your book calls it, the method of relating basis. So we look at this equation we're asked to solve. Ideally we want to try to get each side of the equation written with the same base. And that should be pretty straightforward here. The left side is already written as an e to the 5x plus 2. Now the right side we have the cube root of e. But I remember an old property of radicals. It allows me to rewrite the cube root of e as e to the 1/3 power. Now since we have written e to the 5x plus 2 equals e to the 1/3 power, the only way this equation can be true, since the bases are the same, the only way it can be true is if the exponents are equal. If 5x plus 2 is equal to 1/3. And we solve this by subtracting 2 from both sides. Oh, great fractions. Let's see, 1/3 minus 2, that's 1/3 minus 6/3. So that's a negative 5/3. And then divide both sides by 5. I think I get a negative 1/3. So that's solving a natural exponential function by relating bases. Let's try another one, b. We're going to use that another old property of exponents that I just reviewed a little bit ago. You have e to the x squared, and that junk's being squared. So you can multiply those exponents to get e to the 2x squared equals e to the 8th. And once again, the bases are the same. For this equation to be true, these exponents must be equal. So we just go ahead and set the exponents equal to each other, divide both sides by 2, and take the square root of both sides. And remember, when you take the square root, you have to insert a plus or minus, and square root of 4 is 2. So that's it for solving exponential functions by relating bases. Alright folks, let's take a quick look at another compound interest formula. This is continuous compound interest. Earlier we solved the compound interest formula for any type of compounding period, like annually, semi-annually, quarterly, monthly, weekly, daily. That compound interest formula doesn't work if your interest is compounded continuously. So here's the formula you need for continuous compound interest. All the variables are defined the same as they were before. In other words, P is still principal, R is the interest rate written as a decimal, T is time and year. It's the only difference is that you have the E in here now. So let's do a quick example. You have $10,000 invested at 5.5% interest compounded continuously. How much would be in this account after 9 years? Well, once we see it's compounded continuously, this is the formula we need to use, the continuous compound interest formula. And it's just a matter of substituting in the numbers. The principal is 10,000, so here's your 10,000. Toss 10,000 in for P. E is E. The exponent of e is r times t. R is the interest rate written as a decimal. So 5.5% written as a decimal is 0.055 times t, the number of years. The number of years is 9. And when I enter this into my calculator, I'm so happy to have a calculator to do this, I get the amount of $16,404.98. So that's a quick look at an example of using the continuous compound interest formula. All right, the final topic you're going to see this week are logs, logarithmic functions. To make some sense out of logarithmic functions, we start off by just recalling our exponential function, b to the x. And if I sketch a quick graph, and it looks something like this, I know that point's on the graph, 0, 1. See, I know the domain, let me write the domain here, is all real numbers, and the range is 0 to infinity. And I know I'm talking about an exponential like growth function, so I know the base is a number greater than 1. You know, as I mentioned before, this is a one-to-one function. Because it's a one-to-one function, it has to have an inverse function. In fact, we could graph the inverse function. Let's write down some facts about the inverse function first. The inverse function. Well, the first fact, its domain must be 0 to infinity. Its domain must be the range of the function. And its range must be negative infinity to infinity. Its range must be the domain of the function. So that's one fact. Another fact, if 0, 1's on the graph of the function, then we know the graph of the inverse function must have the point 1, 0 on it. Try to make that a blue color. And then the final thing is, if you remember about the graph of a function and its inverse function, the graph of a function and its inverse function are symmetric about the line y equals x, that line I just dashed in there. So knowing this point is on the graph of the inverse function, 1, 0, knowing the domain of the inverse function is 0 to infinity, so that means the graph is just going to be to the right of the y-axis, and knowing the range is negative infinity to infinity, so negative infinity to infinity, I should be able to take the graph of f of x and flip it about the line y equals x and get a graph that looks like this. That is the graph of the inverse function. The only thing that's missing is to give the inverse function a name. And the name of the inverse function is the logarithmic function. Okay, we just looked at where the logarithmic function comes from. We just basically looked at the fact that the logarithmic function is nothing more than the inverse of the exponential function. We saw the properties. We looked at the graph. We saw the graph. This is an important fact that I'd like you to know. In fact, I need you to know this. If you see y equals, and log is short for logarithm. So if you see y equals log base b of x, that's true if and only if b to the y is equal to x. This little statement helps shows us, or reminds us of the relationship between an exponential function and a logarithmic function, that they are inverses of each other. And I want you to be able to do the following. It's just a skill, and this is a very important skill. I do expect you to be able to go from exponential form to logarithmic form, and vice versa. So for example, the exponential form, 2 cubed equals 8. I expect you to be able to take this exponential form and write it into its corresponding logarithmic form. And it's nothing more than using this fact that I have up here. So when I see 2 to the third power equals 8, I start off by saying, well, that is log base 2. Whatever my base is for log, it's got to be the same as my base for the exponential function. So 2 to the third equals 8. That matches up with log base 2 of 8 equals 3. It's just using this fact up here that I've written down. Let's try another one. 3 to the fourth equals 81. In logarithmic form, 3 to the fourth equals 81 is log base 3 of 81 is equal to 4. I not only expect you to be able to go from exponential form to logarithmic form, but from logarithmic form to exponential form. So if you see this, log base 2 of 32 equals 5. I expect you to be able to write down the corresponding exponential form equation for log base 2 of 32 equals 5. And that would be 2 to the fifth equals 32. So I expect you to be able to go back and forth from exponential form to logarithmic form and vice versa, logarithmic form to exponential form. And it's using this fact up here. Okay, I've said this a couple of times already. I thought I'd write it down for you so you can see it in all of its glory. It's a fact. The function, the exponential function b to the x, it has an inverse function, and that inverse function is log base b of x. Now here's how I'd use that. I mean, it's kind of cool how we can use this. Let's say you're asked to graph the function log base 2 of x. Okay, here's how I could do this. I can do a complete end around. I can basically say, nope, not going to graph log base 2 of x. I'm not going to do that. Instead, I could graph its inverse function. Now remember, its inverse function, the inverse function of log base 2 of x, the inverse function of that would be 2 to the x. So let me make that note. Note. The inverse function is 2 to the x. And we know what the graph of 2 to the x looks like. It's doing something like this. We know the point 0,1's on the graph. We know the point 1,2's on the graph. I mean, we know that stuff because that's one of the first exponential functions that I graphed in this preview video. So I can take the graph of 2 to the x and use it to get the graph of log base 2 of x simply because it's an inverse function. I just have to take this graph and reflect it about the line y equals x. I mean, I know 2 points that will be on the graph. I know the points, oh, let me get this brown chalk. I know the point 1,0's on the graph, and then I know the point 2,1's on the graph. So I get a graph that looks something like, make that bigger so I hit it, something like this. This is the graph of log base 2 of x. Basically all I did was just use something else that I knew, the graph of 2 to the x, in conjunction with the fact that they're inverse functions, and they have symmetry about this line y equals x. And that's it for graphing logarithmic functions. In some of the problems, your e-text is going to ask you to evaluate logarithms without using a calculator, and I could ask you to do the same thing, and I would expect you to be able to do it as long as you remember the relationship between logarithms and exponents. There's a relationship between logarithms and exponents. When I see log base 4 of 64, I mean, think about what that's really asking you. It's really asking you, or let me put in an extra step so you can see what it's really asking you. If you say this represents some number, but you have no idea what the number is, call the number x. That's a logarithmic equation. Put it into exponential form. The exponential form is 4 to the x power equals 64. Rewrite 64 as a power with a base of 4. You can rewrite 64 as 4 to the third power. Then your preservation of equality. Bases are the same. In order for this to be true, the exponents have to be equal. So that means log base 4 of 64 is equal to 3. Just knowing that a logarithm is related to an exponent can take you so far. So when I look at this one here, log base 3 of 1 over 81, I'm already kind of thinking, 3 to what power will give me 1 over 81? 3 to what power gives me 1 over 81? Well, 1 over 81 is the same thing as 81 is 3 to the fourth power. I think I have it. -4. Log base 3 of 1 over 81 is -4. And I didn't write down all the steps in part B that I did in part A because I was just kind of thinking. I was trying to process. It's an exponent, and hopefully I didn't have to write down all these steps. But look, if you need to write down all these steps to get the correct value, that you get a 3 here or you get a -4 here, by all means write down all the steps. I want you to get the correct result. That's the end game. So that's a quick look at evaluating logarithms without a calculator. Alright, you're going to get some basic properties of logarithms in this introductory section on logarithms. The first one you're going to see is log base b of b is 1. So it doesn't matter what the base is. Log base 7 of 7 is 1. So that's property 1. Property 2, log base b of 1 is 0. Property 3, b raised to the log base b of x equals x. And property 4, log base b of b to the x equals x. Those two properties are direct results of the fact that the function f of x equals b to the x and g of x equals log base b of x are inverse functions. Let me show you what I mean. Those two functions are inverse functions. That is a fact. Now remember, when you do the composition of inverse functions, when you do the composition of two functions that are inverse functions, you have to get a result of x. That was our definition of how we knew if two functions were inverse functions. Well, if we crank these two functions through the composition, let's do it. Log of x is the f of g of x, which is the f of, well, g of x is log base b of x. To compute the f of log base b of x, this is just old evaluating functions. Hopefully you're really dialed into the process by this point in the course. You're going to take log base b of x and you're going to toss it into function f wherever you see an x. So it comes in here and you get b to the log base b of x. But because they're inverse functions, we know that must simplify to x. It's because they are inverse functions. And so that's kind of like the meaning behind property number 3 here. To see the meaning behind property number 4, you would do g of f of x. You would do the goff of x. knowing that the GOF of x must also give you x. So if you wanted to derive or see where this property comes from, that's how you would do it. You would do g composed with f of x. So those are some basic properties. Here in a minute, let's do a quick example. All right, I decided to leave the properties up here. Let's quickly crank through this example. Say you're asked to evaluate log base 4 of 4. That's nothing more than using property 1. Log base b of b equals 1. So log base 4 of 4, that's 1. Let's try another one. Let's say you're asked to do log base 8 of 1. Well, that looks like property 2. Log base b of 1 equals 0. So log base 8 of 1, it's nothing more than 0. Kind of looks like a donut, but it's a 0. Try one more. C. 3 raised to the log base 3 of 5. That kind of looks like property 3 here. That says b to the log base b of x. 3 to the log base 3 of 5. So this immediately simplifies down to 5. And there's some quick examples on how to use some of these properties of logarithms. You'll see these. You'll see some homework problems like this in your e-text, like 19 through 26, I believe. All right, just a couple more topics to wrap things up here. You're going to hear stuff called common logs, and you're going to hear something called natural logs. Short and sweet, a common log is a logarithm with base 10. So for example, a logarithm with base 10, that is a common log that you will not see written that way. You will see it written simply like this. When the base isn't shown there, you have to know that it's base 10. So with common logs, the base is 10, and it would just simply be written like this, log of whatever. Now natural logs, on the other hand, natural logs have a base of e. You will not see it written log base e of 5. Instead, you're going to see ln 5. That's an ln 5. And that's short for natural log of 5. You need to know when you see ln, you need to know that the base is e. Just like when you see log, you need to know that the base is 10. And that's a quick look at the common log versus the natural log. Hey folks, final topic as we come back and we look at domains. We're talking about functions. It's natural we talk about domains. Hey, way back when we first started to talk about functions and we started to talk about domains, I told you all that think of a domain as what you can put in for the variable x so that nothing bad happens. And I think I made a list of bad things in function land. I think at that time we saw 0 in a denominator, that would be bad, and a negative number under an even indexed radical would be bad. And I think even at that time I told you that there was a third bad thing in function land, and I said we'll worry about that later on in the semester. Well, here we are later on in the semester. This is the third bad thing in function land. I'll be short and sweet with it. You can't take the log of a negative number. Or 0. You can only take logs of positive numbers. So when you're asked to find the domain of this function, well, you have a natural log of 2x plus 1. You can't take the log of a negative number. You can't take the log of 0. You can only take the log of positive numbers. So whatever you put in here for x, you want to make sure that 2x plus 1 ends up being a positive number. You want to make sure that 2x plus 1 is a positive number. Heck, you just solve this little inequality. there you have the domain. But you know I'm probably going to want you to write the domain in interval notation. So in interval notation, it's parenthesis, -1/2, comma, infinity. And that's the domain. So that wraps up the topics you're going to see this week in college algebra. And as always, this preview video should not replace the actual videos, animations, stuff like that that's in your text. It doesn't replace actually reading the e-text and looking at the videos in the e-text. Hopefully you got something out of this and continue to do good work. Thanks for watching.